This video is about the law of sines. Previously, we've dealt a lot with right triangles, for which we can use our trig functions and the Pythagorean theorem to determine any missing information about our triangle given any other two pieces of information, whether that the information we're given be the angle or the measure of sides or the measures of the angles that we have. However, not all triangles are right triangles, and we may be working with a non-right triangle with which we need to find some piece of information, whether it be the value of a side or an angle, but we can't use any of our trig functions that we've already been using or the Pythagorean theorem because it's not a right triangle, so these don't apply. One of the tools that we can use on general triangles, so of course it also works on right triangles, but for right triangles we have these other nifty tools, we can just use those. So for a non-right triangle, one of the tools we can use is the law of sines. So just for the sake of deriving the law of sines, I'm going to draw in an altitude right here. So remember, an altitude comes out of one angle and then meets perpendicular to the opposite side from that angle. I'm also going to label one of my angles capital B and the opposite side lowercase b. And the other of my angles I'm going to call A, and I'm going to call the opposite side lowercase a. So in this diagram, the capital letters are measures of my angles, and the lowercase letters are measures of sides. Now, the length of this altitude here is h, the height of my triangle. And it's really cool because since my altitude is perpendicular, these are both right angles, which means by drawing in this altitude, I've created two right triangles. Now remember, the sine of an angle equals the measure of the opposite side over the measure of the hypotenuse in a right triangle. So this h for hypotenuse is not to be confused with the red h over here in my diagram for my altitude. Using sine, I can write that sine of b equals my opposite side here, and then in the case of the right triangle right here, the opposite side from b is h, and then I can write that in the denominator. I lied, see, I'm already confusing my h's, so I'm going to rename my height of my triangle here w instead of h. Alright, so for the sine of b, in the context of this right triangle, I can write sine of b equals my opposite side, which is w, over my hypotenuse, which is a, and that's the lowercase a. Similarly, we can write that the sine of our capital A here, this angle, is our opposite side, which is w, over the hypotenuse, which is lowercase b. So in both of these equations, I can solve for w, and then now I've got that a times sine of capital B is equal to w, and that b times sine of capital A is equal to w. So by the transitive property, this is equal to this, so I can write them as such. Now I'm going to divide out a lowercase a and a lowercase b from each side. And I have that sine of my angle b over my side b equals sine of my angle a over the side a. Now, in the event that our triangle was maybe reoriented or we chose our labels differently, we can also add the sine of our third angle c to this set of equations here. However, you'll only really need two of them for any given problem. So there's not going to be a problem, I don't think, in general, where you're going to need to use all three, because you'll be given probably three pieces of information. You'll need to solve for one piece of information, in which case you'll only need one proportion to do that. So we have a theorem, that's the law of cosines. So for a triangle with sides lowercase a, b, and c, opposite from angles capital A, B, and C, respectively, so that's saying that side lowercase a is across from angle A, side B is across from angle B, side C is across from angle C, we have that the sine of our angle A over A, that ratio is equal to the ratio of sine B over the side B, is equal to the sine of our angle C over the side C. Now, for those of you who are interested, I'm going to do an example of an application of the law of sines. Alright, so this is the problem we're going to be doing. An aerial tram starts at a point T 1/2 mile from the base of a mountain whose face has a 60-degree angle of elevation. The tram ascends at an angle of 20 degrees to a point A at the top of the mountain. What is the length of the cable from T to A? Now, the first thing I'm going to do is draw a picture, because if I can draw a diagram, then it's going to be much easier to see what information I am working with, and then apply that information to my, and plug it in to my law of sines to discover the information that I'm looking for. First things first, I'm going to draw my mountain who has a face, so I'm going to be using this as the face of my mountain. It says in the problem it has an angle of elevation of 60 degrees, so I'm going to call this angle right here 60 degrees. And then my tram starts 1/2 mile away, so this distance here is 1/2 mile. And this down here is going to be my point T, that's where the tram starts. And the tram goes way up here to point A at the top of the mountain. So this long side right here is going to be the length of my cable. That's what I'm looking for. Now, the thing that I'm looking for happens to be across from this angle. So you may say, hey, we don't have a value for that angle, but we really can fill it in, because we assume that the ground here is 180 degrees, it's going to be flat, and we're given that this angle is 60 degrees, so that means this angle must be 120 degrees. And one more bit of information, they tell us that the tram ascends at an angle of 20 degrees, so this angle here is 20 degrees. So now we have the value of two angles in our triangle, 120 and 20, so together those add up to 140, and our triangle has to have a total of 180 degrees, making this angle here at side A have a value of 40 degrees. Now, my law of sines says that I need to have the value of a side and the value of the angle opposite to it to set up one ratio, and then the ratio that includes my missing piece of information needs to, I need to have either the value of the angle or the value of that side in order to set up a problem using the law of sines and evaluate. So in this scenario, I have that the sine of 40 degrees over 1/2 mile equals the sine of 120 degrees over C, where C here is the side that I'm looking for. Now I can just use my algebra skills here and solve for C. So we have that C equals the sine of 120 times 1/2 mile over the sine of 40 degrees, and I can just pop that in the calculator, double checking to make sure that my calculator is in degrees mode first, and then I can get the value of my side C, which gives me 0.674, and that distance is going to be in miles. So this here is our final answer for this example. So a moment ago I mentioned that in order to use the law of sines, you only need to set up one proportion, which means you only need one set of information here. And you actually only need 3 pieces of information in order to solve for one piece of information. So you can either have the value of 2 sides and 1 angle to solve for an angle, or you could have a different angle and 2 sides, or you could have 2 sides and an angle. Now it matters how they're oriented about the circle or about the triangle, so just for a quick and easy reference, the cases where you know the values of 2 consecutive angles and then a side, or an angle, or 2 angles with a side in between them, or 2 sides and then an angle that isn't in between them. So these are all 3 cases where the sine, or the law of sines, is going to be useful. So in the other scenarios, we'll be working with the law of cosines and we'll get to that video in a bit. So, if you want to know, hey, can I use the law of sines? Just look for one of these scenarios of given information.